Welcome to On Chemistry. In this video, we are going to see very important inorganic topic, charge transfer, which includes metal to ligand charge transfer, ligand to metal charge transfer, metal to metal charge transfer, ligand to ligand charge transfer, MLCT, LMCT, MMCT, LLCT. What is inside this video? First, we will see types of charge transfer and how you identify them, then controlling parameters. More importantly, we are going to solve 5 representative problems and 5 shortcuts for quick solving. Stay tuned. Here I given a library for the charge transfer. It will help you to solve the problem. It will also serve as a quick reference. Here I given molecules and their types of transition and color. About 70 molecules are given. Make use of it. The simple thumb rule is more number of oxygen mean ligand to metal transfer. Then we are seeing the basics. The charge transfer happen in metal complex system. Metal is central metal atom. Ligands are bonded atoms. Metal represented as M, ligand as L. Totally 4 types known: metal to ligand, ligand to metal, metal to metal, ligand to ligand. Here always charge transfer happen from high energy to low energy. So always acceptor in low energy, donor in high energy. So these are the 4 types. Memorize it. How the electron transfer happened? The important facts are donor acceptor complex. Donor means electron rich part, mostly ligand or anion. Acceptor is mostly metal, which is electron less dense. Here the electron transfer through bond large distance. This creates large distribution of charges. So basically the transition is redox transition, reduction and oxidation. It will happen in UV region. Hence, UV spectra help to find charge transfer. Large change in the dipole moment also happen. These are the basic functions. These are all the basic concepts. Then we will see why the charge transfer has intense color. Because of the selection rule, it has both selection rule, Laporte allowed and spin allowed. Laporte means transition between different symmetry, gerade and ungerade. Spin allowed means there is no change in the total spin. So both rules are allowed, so highly intense. Hence, molar extinction coefficient is high, about million times, like dyes. Example is potassium permanganate. If you add a drop of it in water, you will have high intense purple color. We will see one by one. Metal ligand charge transfer. The name itself saying the charge transfer from metal to ligand. Metal is donor, ligand is acceptor. How the metal should be? Metal should be with filled orbital, low oxidation state and oxidized during the transfer. Ligand should be on low energy, should have empty orbital to receive the electron reduced in the transfer. Mostly organic ligands involved in the metal to ligand charge transfer. Example, ruthenium piperidine complex. Then we will see ligand to metal charge transfer. Here metal and ligand behave differently when compared to MLCT. Metal should be of vacant orbital, very high oxidation state, reduced during charge transfer. Here ligands will be filled orbital, mostly bidonor ligands, and oxidized during the process. So ligand is the donor, metal is the acceptor. Examples are potassium permanganate and dichromate. The most possible ligands are oxides, sulfides, halides, selenides and acids. So simple trick would be metals with high oxidation state will undergo ligand to metal charge transfer. Then the rare one, metal to metal charge transfer. Here two metals will be there. Charge transfer from high energy metal to low energy metal. Here one metal behave like ligand, one metal behave itself. The first metal will be vacant d orbital, high oxidation state, and it will be reduced. On the contrary, other metal filled orbital, low oxidation state and oxidized. Here mostly charge transfer happen through bridge ligand. The example will be Prussian blue complex, that is Fe4 FeCN6 thrice. Here metal is ion with variable oxidation state 2 plus and 3 plus. So charge transfer from Fe2 plus to 3 plus. Then the next one, LLCT, ligand to ligand charge transfer. Normally two ligands will be there. One ligand behave like metal, other behave like ligand itself. The donor will be electron rich, filled orbital, oxidized during the transfer. Acceptor ligand will be electron poor, high oxidation state, reduced during the electron transfer. Normally big ligands has ligand to ligand charge transfer because it happen as intra. Mostly metal act as a bridge, help the electron transfer. Here I given the example ruthenium bipredyl sulfide complex where charge transfer between bipredyl and sulfide. Then we are seeing the few basics which help you to solve the problem. First one will be energy levels. Normally, the metals will be of different charges. Higher charge will have low position of the orbital, that is LUMO, which makes the electron transition very easier. So more charge mean which create more electronegativity, less energy required for the transition. Here if you look at it, vanadium 5 plus, chromium 6 plus, manganese 7 plus. Manganese is with higher charge, chromium on 6 plus, chromium next, then vanadium. Manganese will be low charge, vanadium will be higher charges. So more the charge, lesser the energy would be. Then energy level between the D block elements 3D, 4D and 5D. 5D has higher energy difference when compared to 3D because of effective nuclear charge and other reasons. Simply you memorize 5D has higher energy when compared to 3D. So master the energy levels. Then the color. Color normally happen if the compound absorb and emit in the visible region, that is of low energy. If compound has high energy between the transition, then lights pass through it, don't absorb it, become colorless. So simple fact is higher the energy difference, mostly colorless, lower the energy difference, mostly colorful. Let us see the first question. Arrange the following compounds with respect to LMCT, that is ligand to metal charge transfer, in terms of energy. The compounds are VO4 3 minus, CrO4 2 minus, MnO4 minus. So let us break the problem. All have same ligand, that is oxygen. So answer is in the metal. If you look at the metal, write the metal with charges vanadium 5 plus, chromium 6 plus, manganese 7 plus. As we seen already, larger the positive charge, higher the electronegativity. So low will be the metal ion. Ligand will be of same charges. So charge transfer occurs. Vanadium with higher energy, chromium get lower because of charge, manganese will be still lower. So energy transition for manganese is lesser than chromium, then vanadium. Then the next question, MnO4 minus is deep purple in color, whereas ReO4 minus is colorless. This is due to the greater energy required for the choices are DD transition in rhenium compound, DD transition in manganese compound when compared to rhenium, charge transfer from oxygen to rhenium compared to oxygen to manganese, charge transfer from oxygen to manganese when compared to oxygen to rhenium. Here MnO4 minus rhenium O4 minus is given. Ligand is same, so answer is in the metal. We write the metal with charges. Rhenium O4 mean rhenium 7 plus, manganese 7 plus. Here no d electron in both the compound, so answer cannot be dd transition. So answer is between C and D. The only difference both has is orbital. Manganese in the 3D system, rhenium in the 4D system. So energy difference, if you look at it, rhenium has very high. So the answer will be on energy difference, where rhenium is higher, light pass through it, so it is colorless. So answer is C. Then the next question, cadmium sulfide, mercury sulfide, bismuth iodide are colored due to ligand to metal charge transfer, metal to ligand charge transfer, DD transition, combination of both LMCT and DD transition. Here ligands are different, metals are different. If you look at the metal has common phenomena, that is all are D10 system with 2 plus charges. Cadmium 2 plus is D10, mercury 2 plus is D10, bismuth 3 plus is D10. So there is filled d orbital, no transition is spin allowed. So answer cannot be C and D. So only between 1 and 2. If you look at the B, metal is in low oxidation state and it is not possible. On the contrary, ligands are bigger, sulfur and iodine polarized can donate the electron better. Further, ligands are filled orbital, that is S2 minus is octet, I minus is octet. So only possibility is LMCT. So our answer is A, LM charge transfer. Then the next question, the dark purple color of KMnO₄ is due to DD transition, ligand field transition, charge transfer transition, sigma to pi star transition. Here if you go by the basics, KMnO₄ metal is manganese which is in 7 plus oxidation state. You solve by the basics, X will be 7. It will be of very high oxidation state. Oxygen is the ligand. It can be a donor filled ligand. So the possibility of ligand to metal charge transfer, simply charge transfer, but we should analyze other options. Here manganese 7 plus is D0 system, so no DD transition is possible. No d orbital, no DD transition, no pi bond in the system, so no sigma to pi star transition, and field transition means it is mostly not possible, at least not in the visible region. So only possibility is charge transfer transition. Then the final example. Arrange the LMCT energy of following compounds: mercury chloride, mercury bromide, mercury iodide. Here we break the compound cation and anion. Here metals are same. So answer in the ligand. Let us write ligand with charges chlorine, bromine, iodine. Same number of valence electron. So only possibility is size and electronegativity. Chlorine is more electronegative, hence it will be of lower charges. Bromine is next, then iodine. So if you write difference in energy, chlorine has higher, bromine comes next, then the iodine. So the order will be HgCl2, HgBr2, HgI2. Finally, we summarize with tricks. First one is higher the metal charge, mostly ligand to metal transfer. Then filled orbital, that is S2 minus O minus mean ligand to metal transfer. If it is a biological ligand, you may guess it is from metal to ligand. If you have same metal with different charges, then metal to metal transfer, that is MMCT. So the rare one will be ligand to ligand transfer, that is in hemoglobin. There is no shortcut for that. Then most common and useful trick will be more number of oxygen, ligand to metal transfer charge transition occur.